welcome to Chemistry at Hononegah High School, and today we are finally looking at our last ideas related to Chapter 3. And one important aspect of chemistry that involves math and calculations involves the idea of graphing and graphical analysis. So we're going to include this idea in our Chapter 3 discussion. So graphing is using data to create a graph to help you reveal patterns if they exist. When you're looking at a list of numbers, sometimes the trends and patterns that exist are much easier to see when you're looking at it in graphical form. So it's a visual way to represent what it is we're talking about. So it's a visual display of data that helps us see trends and understand ideas better. Now, the first type of graph that we're going to discuss is called the circle graph. And a circle graph or a pie chart, you can use the same thing or either name, they're interchangeable, is basically a piece of pie that's divided into wedges, or pie, like a pizza or a pie is divided into wedges, and the actual size of each of those pieces shows a part to whole relationship. So a circle graph is really most useful when you're showing parts to a fixed whole. So we've got all these different things that add up to make a whole. The single easiest way to look at that is a pie chart or a circle graph. And it's really limited. That's about all we really use it for, but it does that extremely well. Now, the parts are usually labeled as percents with a circle representing 100%. Now, sometimes they won't show it as percents, but it might be maybe the total was 100 grams. And then you would show each one as how many actual grams that was compared to the overall 100. But technically, it really doesn't have to be 100 if we're not dealing with percents. But that's our simplest type of graph that we use in chemistry, and it really has just one application, looking at parts to a fixed whole. Does that extremely well, but it really doesn't do much else. Now, the next type is a bar graph. And a bar graph is often used to show how a quantity varies with another factor. So we're looking at the relationship between two factors, such as time and location or temperature. In this particular case, we're looking at the relationship between how much rain we got in the different months throughout the year. Now, in the case where we're really looking at these two things, one of these variables, if we relate this to what we talked about in an earlier chapter, the dependent variable and the independent variable, that's really what we're looking at here is the relationship between the dependent variable and the independent variable. Now, in cases where we're looking at the relationship between those two things, we put things in a very specific location. We always put the dependent variable on the y-axis. And then the independent variable, what our experimenter is controlling, would go on the x-axis. So in the case of this, what our experimenter really controlled was, I'm going to measure rainfall per month. So my months then have to go on the x-axis because that was what he was controlling. I'm looking at this month or that month and so on. He really didn't have any control on how much it rained over those months. That would be the dependent variable. During this month, what was the average rainfall? So remember, when you're looking at this kind of graph, the axis tells you what's the dependent and independent variable. Hint, expect to be able to tell me that, not only for the homework, but on the test for some different graphing relationships. So dependent variable, what changes as a result of the experimentally controlled independent variable, we always put on the y-axis. And what you control as the experimenter, you're going to put on the x-axis. And the relative heights of the bars show how the quantity varies. So sometimes patterns jump out at you, like you can see here. What are the, in general, rainy months? June, July, August, September. Those seem to be by far the rainiest months in Jacksonville. And that happens to correspond with probably monsoon season. Now, the final type of graph, which is the one we really use most often in chemistry, is the line graph. Now, line graphs can often be used to show the same kind of information as a bar graph can, but it does it for very specific relationships that we're looking at. So in some ways, you can use a bar graph or a line graph. It really just depends on what we want to get out of it. So in chemistry, most graphs that you create and interpret are really going to be line graphs. The points on the line represent the intersection of data between two variables. So at this mass, what is its volume? At this mass, what is its volume? And those give us graph data points on this graph. Now, the dependent variable, once again, is always going to be plotted on the y-axis, and the independent variable is going to be plotted on the x-axis. So this is just like with a bar graph. If we set it up that way, we always know what's what by just glancing at the graph. So in this particular case, mass must be my dependent variable, and what I must have controlled was the volume. So I said, okay, at 10 centimeters cubed, what is my mass? And then I measured it. And then I said, okay, at 20 centimeters cubed, what is my mass? And then I actually found the weight experiment of that particular volume. So if my graph is set up this way, the experimenter controls the volume, and what changes as a result of it is the mass, my independent and my dependent variable. Now remember that the independent variable is the variable that the experimenter changes or controls during the course of the experiment. So what is it you're changing is the independent. What changes as a result of that is our dependent variable. And just like with a bar graph, they're always found in the same place, x and y axes. Now sometimes points are scattered and you're not going to get a perfect line to fit through them all. Well, pretty much in every case when you're dealing with experimental data, there's going to be uncertainties and errors, small ones, so you're not going to get a perfect line that goes through them. So what we draw is what's called a best fit line. So we try and equally split the points so we have an equal distance above and below the line for all of our points. So this is what's actually known as an averaging technique. Drawing that best fit line is actually an averaging technique. And that's actually something that we're going to test on the density lab. Now, if the best fit line is straight, then that means there is a linear relationship between the variables, and the variables are called directly related. Now, I'm not saying it goes uphill or downhill. I'm just saying that when we look at our plotted points, there's a clear best fit line that can be drawn through them. So our dots seem to make a linear relationship. That would be known as a direct relationship. Now, we can talk about the steepness of that relationship, which would be what's known as the slope of the line. And usually when you're doing line graphs, one of the things that we want to calculate is the slope. Not in all situations, but many of them. That's really why we're doing the bar graph, or the line graph, is to actually calculate the slope. But we can also use it to predict within a set of data points, what would the different other points be? If I know this independent variable, look on the graph, where would that be as a dependent variable? So I can check, where my y-axis, or on the x-axis where a point is. And if I've got a best fit line already drawn, I can say, okay, at this particular value, what would my value be? And I can also extend above and below to make predictions. Or I can end up finding out what the slope is, which is oftentimes what I'll do when we're doing a line graph. Now, if the line rises and to the right, it has a positive slope. And as one variable increases, the other is going to be increased. So that would be a directly related set of variables with a positive slope. Now, if a line sinks to the right, then the slope is negative. And a negative slope indicates that as the dependent variable decreases, the independent variable is going to increase, and vice versa. So it shows an inverse relationship between the two. As one gets bigger, the other gets smaller. Now, either way, the slope of the graph is constant. So if we look at our points and we can see it looks fairly linear and I draw a best fit line, that means the slope is actually constant for those. And remember, the slope from math class is the change in y divided by the change in x. So this is the equation that you've seen before. This should look familiar to you from class. So if we know our 2 points on that line, we can use it to calculate what the slope of the line is. So change in y over change in x is how we often find a slope. Now, remember, what we're really looking at is an organized way to help understand information. That's what all these different graphs are. So there are certain things that we can understand when we're looking at somebody's graph set of data, especially a line graph. First, we can identify the independent and dependent variables based upon a graph. That's something you should be able to do. Remember, the independent variable is our x-axis, and the dependent variable would be the y-axis. So what we graph on the y-axis is going to be our dependent variable. What we graph on the independent, or on the x-axis is going to be our independent variable. Next, when we're trying to make a line graph, besides establishing what goes on what axes, we can look at the ranges of data and use that to consider what measurements were taken. Now, if a graph has multiple lines or regions, we really study one at a time. So let's say we're looking at a relationship between several things, and that was one set of data, and that was one set of data. We don't combine the two. We look at them separately and treat them separately. Now, one of the things you should also be able to do is decide if the relationship between the variables is linear or nonlinear. So when we graph our points, do you see that it follows a straight line, or are they scattered all over the place? And when we just put our points on the graph, that's known as a scattered plot. And when we look at that scattered plot, if the points seem to be following what's a relatively straight line, then we would know we have we have a linear relationship. If our points are just all over the place, then we would have what would be considered a non-linear relationship. And sometimes, and you're probably not going to see this in this year, but let's say we graphed our points and we saw something that looked like this. So it's not linear, but definitely follows a curved path. So that would be a nonlinear useful curve situation. We're just not going to see that. But another thing you should be able to look at is, if the relationship is linear, is the slope positive or negative? Those are all things you need to be able to think about and understand when you're looking at a graph. Now, when the points in the line are connected, the data is then considered continuous. So we didn't take data points at every single point, but once we draw our best fit line, we now have a way to interpret all of the different measurements that we didn't take. So you can read the data from the graph that falls between the measure points, and that's known as interpolation. So even though we didn't actually measure the mass and volume at all the different volumes, we can use our best fit line to actually determine at any given volume what the mass would be. And since we're looking within our data point, that's known as interpolation. Now, you can also extend the line below and above the data that we collected, and now we're looking at outside of our data points to make a estimation of what the value might be, and that's known as extrapolation. Both interpolation, looking within your data set, and extrapolation, looking without your data set, are very valuable tools in everyday life. But one thing to remember is extrapolation is a little less reliable than interpolation is, because interpolation, we've got data sets that are around those points where we've got a good instance to say, well, it looks like the trend is constant in this region. When you extrapolate, what would happen if it went from a linear relationship to a nonlinear relationship at some point in time? So remember, extrapolation involves a little bit less precision than interpolation does, because who knows, maybe you might end up with a situation where the relationship changes and it's no longer linear. So why might extrapolation be less reliable than interpolation? Well, because extrapolation is outside of our data set, and maybe our trend changed after a period of time. So that trend might change. And that finishes finally our notes over chapter 3 in chemistry.